This is Jack Jackson. In this video, we're going to introduce another class of applications where we can use derivatives to help us solve problems. And this class of applications are called related rate problems or related rate applications. Now, basically the idea here is we're going to come up with a relationship or between two different rates of change. So we often find a place where we have some quantity, let's say F is changing, as another quantity, say U is changing, but in turn the quantity U is dependent on the third variable changing, usually time, say T. So delta F depends on delta U, but delta U depends on delta T, so ultimately delta F depends on delta T. So both F and U are changing with respect to time. And so if you remember, this is investigating this situation is exactly what led us to the chain rule. So the chain rule is definitely going to be related closely to this concept. And so what we're going to be looking at in this video is physical applications where we have two variables which are related to each other, and both are dependent on the third variable, almost always time. And the basic steps then are the following. So here are the basic steps for solving related rate problems. First of all, you read the problem. Always a good place to start, and just try to get an idea of what's going on. And of course, the first thing you're going to do is just identify maybe that it is a related rate problem. Now, the next thing you're going to do is represent your information. Oftentimes, we're going to draw a diagram and label the parts, or maybe even isolate a part of the diagram and draw it. That's going to be very crucial in some cases. In some cases, it's not going to be needed at all. But what you're always going to have to do is identify your known and unknown values. Whenever you are given a problem like this, there are probably no letters in it at all. There's no X, there's no Y, there's no F or U or T or V or anything else. So you put in letters that you want to put in. And typically we'll use letters that represent the quantities. If we're talking about a velocity, we'll use V, or maybe if it's a volume, we might use V. Or if we want to talk about a height of something, we'll use a H. Or if we're using time, we'll use T. So we'll label the meanings of these things, and some of these, one of them might be a rate of change that you know, and typically one is known. And there's another rate of change, usually both with respect to time. One you know, and one is the one you're looking for. Okay? So don't worry about the rates of change at first. The first thing then you do is write an equation that represents a relationship between the two quantities. So between, say, the F and U, for example. And then what you do, so that one will not have derivatives in it. Then what you do is you take the derivative of both sides with respect to whatever the third variable is. It's almost always time. And so you'll use the chain rule here because both of the original things depend on time. They change as time changes. Okay, so be sure you treat them as variables and apply the chain rule. Well, that chain rule is going to lead to, say again, if our variables are F and U, that'll lead us to a dF over dt, and also a du over dt. And what happens is, so now we have an equation. It's a differential equation, I guess, because it has derivatives in it, but it's a related rate equation. It's an equation that relates two derivatives, two rates of change. Okay, and then what you do is you substitute in the stuff that you know, what values of the variable you know. If you know, and one of the derivatives you probably know at that point, and then it's the other derivative that you're trying to solve for. Be very careful to wait until this step to substitute in the given information. One common mistake made with this kind of problem is to try to substitute in values, say, for one of the variables earlier on, turning them into constants before you take the derivative, and that's not what you want to do. And of course, once you solve that for the original for the derivative that you're looking for, then you've solved the problem. So let's try this for an example here. So the weekly cost, C, in dollars for a manufacturer to produce Q automobile tires is, say, approximated well by this quadratic formula here, quadratic polynomial function. C of Q equals 2,100 plus 16Q minus 0.01 Q squared. And at least for Q's going from 0 to 800, this is a pretty good model. So if 400 tires are currently being made per week, but production levels are increasing at a rate of 20 tires per week, compute the rate of change of cost with respect to time and the total cost at this point. Well, they've already done a lot of the work for us by giving us this relationship, this equation that involves both C and Q. So we got C equals this quadratic polynomial in Q. Now, but both quantity and the cost, both the quantity that you're measuring and the cost that it takes to measure those is changing as time goes on. So we want to take the derivative of both sides here with respect to t. Of course, derivative of c with respect to t is just dc over dt. And here, though, we can use the sum rule. The derivative of 2100 is 0. That's a constant, so that derivative is 0. Derivative of 16q is 16, but then times dq over dt from the chain rule. Derivative here is 2 times the first part, which is negative 0.02. The q goes down the first power, and then you have a dq over dt. Now, these are multiplications here. 16 times dq over dt, and multiplication here. So we can use the distributive property to factor that out in our common factoring there, distributive property factoring. And so you see that you get this line here. Well, now we have a relationship that has both dc over dt and dq over dt. Now let's look what we're saying. We know that at a particular point, if we're making 400 tires, now what's 400? Well, is that a q, a c, a dq over dt? What is it? Well, that's the actual number of tires per week. That's a quantity. Okay, so that goes in place of the q right here. Okay, but the production levels are increasing at 20 tires per week. So the 20 tires per week is the change in the quantity over time. Change in the weekly quantity over time. So that's dq over dt. Well, now notice we have everything on the right side. We just work that out by hand or on a calculator. And that turns out to be $160 per week. And the total cost at that time, okay, notice if we have 400 items, we can put it in this formula right here, in the original formula there, and we see that the total cost is $6,900 really per week. And this is $160 per week really. The cost is already, we're only talking about 1 week at a time here. So that's the weekly, C is weekly cost, so it's dollars per week. C prime then would be dollars per week. Okay, let's do another one here. The annual demand, Q, for bottles of wine from a vineyard, when the bottles are priced at P dollars each, satisfies the equation Q times e to the 0.04 P equals 6,000. Notice how lucky we are this time. They actually told us the formula that relates Q and P to each other. The price is currently $12 per bottle. Find the rate at which demand changes with respect to time if the price is currently increasing at a rate of $1.10 per bottle per year. Now, notice it's per year, so we're going to be measuring time in years. So as time goes on, both the price per bottle is changing, and it's increasing, so that it's inflating, and the quantity then is going to change too. Okay, and what would we expect the quantity to happen if the price per bottle is going up? We'd expect the quantity to to go down a bit. Okay, so let's see if all that works out. Resist the temptation to start plugging in the 12 and the 100 and the $1.10 somewhere. Okay, we do that later. Okay, so we take the original formula, which is here. I actually solved Q on one side, P on the other side first, so I can avoid the product rule. So I multiply by the reciprocal here, which is e to the negative power, makes this 1 times Q on the left, and that makes this power negative on the right. So then I take the derivative of both sides with respect to t, and the left is just dq over dt. And the right side, I can use the constant multiple rule, brings the 6,000 out. Then this is derivative of e to the u is e to the u times the derivative of the u, which is negative 0.04, times the derivative of the p, which is dp over dt. So negative 0.04 times 6,000 is negative 240. I've got e to the negative 0.04p dp over dt. So there's our equation that has our related rates in it. It's giving a relationship between those two rates. Now, once we have that, now we plug in. At the point we know that it's $12 per bottle, that goes in for P right here. And the rate of change, $1.10 per bottle per year, is the rate of change in the unit price. Okay, so that goes here for dP over dt. Well, now we know everything on this side. We just work that out. I'm going to use a calculator to approximate this. And I get negative 163.3588154. That's negative. It says that over time, we're going to be selling less as that price goes up. Okay, that seems maybe reasonable. And at the current time, the price is $12 per bottle. The demand is, well, I just plugged that in the original thing here to solve for Q. Actually, I did it in this version where I'd already solved for Q. And that turns out to be about 3,713 bottles per year, and the price is increasing at $1.10 per bottle a year, and the demand is decreasing by about 163 bottles per year. All right, let's try another one. Suppose that an oil spill is spreading out in the shape of a circle with radius r. The rate of change in the radius is given by 5 over r. At time t equals 7 hours, the radius is 500 meters. What's the rate of change in the area of the spill at this time? See if you can work this one out. Press pause now. Okay? Notice that this time they did not give us the relationship in terms of the r, between the r and a. So we have to work that out. So let's introduce some variables. So notice that t is going to be time in hours. They kind of already gave us that variable. R is the radius of the circle. They kind of gave us that, and it's in meters. Okay. Notice that radius is in meters there. T was in hours because of this here. A is the area of the spill, and of course if the radius is in meters, then the appropriate unit for area would be square meters. R prime of t, or dr over dt, is the rate of change in the radius with respect to time, and A prime of t is dA over dt is the rate of change in the area with respect to time. And of course the thing that you need to know is the thing from geometry, that the area of a circle is given by pi times the radius square. A equals pi r squared for a circle. Both A and R are functions of time, so we really have A of t is pi times r of t squared. So what I'm going to do is I'm going to look at it just this way. Take the derivative of both sides with respect to t. The derivative of the left is just dA over dt. The derivative of the right, pi is a constant. The derivative of r squared is 2r. So that's 2 pi r. But then the r is not t. It's a function of t. So we have to apply the chain rule to get dr over dt. Or write it out as the same way here. A prime of t is 2 pi r prime of t is another way to say it. I prefer kind of the second way. Now we can substitute what we know at a particular time. So at a particular time, t equals 7 hours, the radius is 500. So we can plug in r as 500. And we're told that the dr over dt is 5 over r. So 5 over r at that point is 5 over, well, the r is 500. So that's 100. And so we get that. So what does that give us? That gives us dA over dt is the thing we're looking for, which is 2 pi times the r of 500. Actually, I could just go back here without that formula 5 over r. I can just go ahead and put that in. So it's 500 there, and this is 0.01. You multiply all that out, you get about 31.4 square meters per day. Okay, let's do some more in the next video.